So this video we're talking about frequency and probabilities, covering frequency trees. So if you remember last video, I talked about flipping a coin, right? And we have a coin with heads one side and tails the other side. And I talked about how, say, the probability of heads, for example, will be a half, right? Because, or 50%, or even 0.5. Let's have all three. And the reason we said this was because the number of outcomes there are two outcomes and one of them satisfies a condition, right? So it's probability is a half. But another way of thinking about probability is actually saying if we flipped a coin many times, let's say 10,000 times, right? Of those, if we flip them, say number of flips, right? Of those, how many would kind of be heads? And that's how we'd figure out the probability of heads. We'd say, over loads and loads of times, the number of heads divided by the number of flips, this is the probability of it happening. So basically, if you're running the experiment, i.e. flipping the coin, multiple loads and loads of times, so say 10,000 times, and eventually what you should get is you should find that the number of heads you get is a half on average of kind of the number of flips that you do. And kind of this is another way of thinking about what probability is. That it's like, if we generalize this, we say P of outcome is number of outcome. So i.e. in this case, the outcome is head, the number of heads, so number of outcome, over number of experiments. So it's basically saying, if you do something so many times, right? On average, what's the kind of how many do you get of those, right? And when you divide the number of outcomes by the number of experiments, what you're getting is like effectively another way of thinking about what the likelihood of the next flip being the next kind of experiment being the outcome you want. So, or in our heads and tails case, the next next flip being the heads. So this is just another way of thinking about probability. It might be it's a bit less intuitive than kind of the number of outcomes, kind of the outcome you want over divided by the number of equally likely outcomes. And what we get is also, if we say, if we had something like a table such as this, so a table say something like this, right? So say we roll a dice 10,000 times, and the number we get, so say the face, the face could be 1, 2, 3, 4, 5, or 6. And kind of this, if this is the face, and this is kind of the number of times we get that face. Of times. So say, if we say we do it 1,000 times, right? Say we get the 1,165 times, and a 2,167 times, and a 3,166 times, and 4,167 times, a 165, and 6 is 170, which adds up to 1,000. So you might be thinking, what's the probability that we get a 1? Well, if we think about this, if this was kind of using this data only, right, we don't necessarily know if it's a fair dice. So if we say the probability of getting a 1 is, well, the number of times we get a 1 divided by the number of times we tried, right, looking at a formula back here. So the number of outcomes that we wanted divided by the number of experiments divided by 1,000, which is, 0.165, and then we can actually repeat this for all of them. So we do kind of probability here, and we're dividing each of these by 1,000, right? We can kind of repeat this process. So you get 0.165, 0.167, 0.166, 0.167, 0.165, 0.170, and we can see that these are kind of roughly equal, right? If it was a fair dice, we'd expect a sixth, and a sixth is 1 divided by 6 is 0.1666 reoccurring, right? It's that number there. It's we'd expect 0.16 if fair. And with 1,000 we get something fairly close to it, but sixes, there's quite a lot of sixes, right? So way more than expected compared to everything else. So this is 0.17. So that's what, 4 more. So if we would expect, for 1,000, if the probability is that, we'd expect 166.6, right? So even 167. So that that's 3 kind of more than expected, I guess, right? So you might be thinking, does this mean that the dice is fair or not? Well, this kind of depends. There's actually some statistics that you learn at A level to kind of check this if you want. But basically, we can say this seems fairly fair to me, kind of just looking at it. And also, we've only done 1,000, right? 1,000 rolls. If we do, let's say, 10,000 rolls, we'll get even closer to, we're more likely to get to kind of the kind of a numbers representing a probability of a 6, because as if you roll one, right, you might just have something. Let's say you only roll 10, right? If you roll 10, I actually encourage you to actually go ahead, if you have some dice at home, try this out. If you roll 10, roll dice 10 times, what you'll get is probably kind of like quite a skewed numbers. You might get say like 3 2s, and maybe, I don't know, no 6s even. And from that you might think, oh, is the probability of getting a 6 0? Well, that's because you haven't rolled them enough times. Because at in small numbers, right, when you roll it, say, 10 times, the random chance makes a big difference on the probability you calculate. But as you roll it more and more and more times, right, you approach the kind of the statistical, the kind of theoretical expectation. So if it's a fair dice, right, you can't say if you roll it 6 times and you don't get 1 2 3 4 5 6, right, one of each, which is what you kind of expect, right? If it was if it's fair, there's an equally likely thing, right? So if you roll it 6 times, maybe you should expect 1 2 3 4 5 6, but you won't get that. That's because kind of the random chance actually plays a part in these small numbers. But over kind of larger numbers, eventually you'll kind of get to the expected kind of the probability that's more representative, I guess. That's a way of putting it. So basically, the moral of the story, and after all these kind of a bit of rambling, is that you need to do a lot of experiments, and the more experiments you do, the closer you get to kind of the true distribution of the probability. And when I say distribution of the probability, I mean the distribution of the probability here is that each of these would be equal if it's a fair dice. But if it's if with small numbers, you might see a distribution that's heavily skewed. You might you might see, let's say if you only did 10 rolls, right, you might see, for example, you might see 0 of 1, 0 of 2, 3 of these, 2 of this, 4 of these, what is that, and then 3 of these, right? And then you might say, oh, probability of 1 and 0, which is, again, as I mentioned, that'd be kind of incorrect, right? Well, not incorrect, but kind of, that wouldn't be the true probability, or the true distribution. So you'd have to do quite loads and loads of rolls, basically. So this is kind of a distribution, a table, and we can use these tables to kind of figure out the probability, provided the number is large enough. So there's also these things called frequency trees. So in this case, we've got 100 students who had some homework. 42 of those students are boys. 8 of the students did not do their homework. Poor form. 53 of the girls did do their homework. A uses information to complete the frequency tree. Okay, so this frequency tree is saying, look, there's 100 in the beginning people, 100 kids. And of those boys, how many boys are there? Well, that 42 comes here, so there's 42 boys. That's what this thing is saying. This branch left is basically saying, let's split this 100 into boys and girls. There are 42 boys, and how many girls? There are 100 minus 42, which is 58. So there's 58 girls. Now we split the boys again into those who did do their homework and those who did not do their homework. And same thing with the girls. So we know 53 of the girls did do their homework, so 53. So that means 5 did not do their homework. We know there's 8 total students who did not do their homework, and 5 of those are girls, so we know 3 of those must be boys. Oh, sorry, I got that in the wrong order. 53, 5. So there must be 3 boys who did not do their homework, and if 3 boys haven't done their homework, and there's 42 boys, and we know the rest of them have done it, that means 39 boys have done their homework. So basically, this frequency trees, as a recap, is you kind of take kind of a certain number of things, so in this case a certain number of students, and you split them into kind of these interesting, I guess, classes, right? Or interesting boxes, I guess, even. So you might think of, how many of these are boys? This might be something that's we're interested in. And how many of these are girls? That's another thing we're interested in. And another thing that we are interested in if they did their homework or not. So we split them again. If you think about it, we could also represent this in kind of, we could do, 100 students, and then those who did homework, did not do homework. I'll just write HW, and then boys, girls. Which is kind of, which is a very similar thing. Sorry, G should be here. G. Yeah, so which is, as you can see, this is kind of just in reverse, which is kind of, you'd get similar, well, you'd actually have pretty different numbers here, but you could also do this, for example. So, why have we done it in this order? I guess, this is, I'm presuming to kind of say, think if the gender of the student has any impact on whether they did homework or not. And we're seeing, 3 out of 42 boys did not do their homework, whereas 5 out of 58 girls. If we look at the proportion of boys who didn't do their homework, right, we think 3 divided by 42, that's 1/14. So proportion of boys who did not do homework is equal to, say, 1/14. And, the proportion of girls who haven't done it is 5/58. So it looks like, 5/58, and if we kind of compare those numbers, 5/58, if I'm not mistaken, 5/58 is actually a bit larger than 1/14, so it looks like, there's a higher proportion of girls who haven't done their homework, for example. And another thing that you might be asked to do with these frequency trees is say, suppose we pick a person, for a boy at random, right? What's the probability, he hasn't done his homework? Well, okay, let's say we pick a boy at random. So there's 42 boys, and it's equally likely that you're going to pick a boy, right? Equally likely you'll pick any of the boys in that group. Of those, 3 haven't done their homework, and 39 have. So probability that you've picked a boy. So, and what's the probability they've done their homework, provided they're a boy? So P done homework, given they are a boy. Well, we think, okay, there's 39 students, so there's 42 boys, right? So, and how many of them have done their homework? Well, 39, right? So this is what we think about what our probability might be. So frequency trees are useful insofar as that they can help you kind of think about the probability of picking, if you were to pick someone randomly from that sample, or sample as in, because it's 100 students that we're thinking about, that's a sample. 100 of a certain school, for example, these students probably all go to the same school, right? So we think, of these 100 students, if we were to randomly pick, say, a boy, what's the probability they've done their homework? Or if we were to pick a girl, what's the probability she hasn't done her homework, or she has, for example? But the thing is, of course, this only applies to, say, the students, right? You couldn't say the probability of a boy in the whole world who hasn't done their homework based on this kind of information, because I obviously say that depends on kind of, what school they go to and how much, how strict is their homework enforcement, and depends on their parents, etc., right? So you can do the probability of picking a student from this sample and kind of use this frequency stuff here to think about the probability, but you can't use this probability results and say that they hold for kind of different situations. So with probability, kind of, I guess, compared to other mathematics, when you do probability statistics, there's a bit more kind of critical thinking on your behalf involved. You kind of have to sometimes think things through a bit more than, or think things through a bit more deeply than some other math. So you can't just kind of always blindly follow the formula. Just you have to think about, because a lot of, intuitively you do know a lot about probability. It's just kind of using that and bringing that forward. You know that one student, students at one school are going to be different from students from another, for example. It's just kind of using that information that you already have to in these circumstances. But this question didn't ask that. That was just a bit of extension on my part. So hopefully that all made sense, and I'll see you guys in the next video.